We're going to look at how to simulate stock prices using geometric Brownian motion. Now I've got two files open. One of them is the prices2 file where we calculated these geometric Brownian motion parameters, mu hat and sigma hat, from monthly data on the SPY stock index fund. Also got open this file here, which was where we previously used a log normal distribution developed from the multiplicative returns to calculate a stock price after 5 months. Also calculated the 5% VAR and conditional VAR. I'm going to set up the GBM simulation in this same file. Now, here are the mu hat and sigma hat parameters in the Python file. We could download these to Excel, but for now I'm just simply going to copy these over. And so we will put out here in this file the mu hat parameter and sigma hat, and I'll just copy these numbers in. I copied them, you could also type them. Now, we'll do this two ways. The first thing we'll do is set up a daily simulation, and then we'll also set up a monthly simulation. So let's set up first the daily, and what we're going to do is set this up to simulate the price 5 days out. So we'll just note that this is 5 days. All right, and so the beginning price is going to be the same beginning price we used previously for the other simulation. In this case, what we're going to do, instead of the return, we're going to use a standard normal random variable, and I'm just going to use Z as the notation for that, which is the same notation in the textbook. And this is going to be a distribution, and it's going to be a standard normal distribution. So let me define a normal distribution. We'll find normal, it's right here. And a standard normal distribution is one with a mean of 0, which is what's in here, and a standard deviation of 1. So we need to change that to 1. And so now that's a distribution. And then we use that distribution and the GBM parameters to calculate the end price. Now we will use one other value, and that is the delta for the simulation of the daily prices, price after 5 days, is going to be 5 divided by 252. 252 is the number of typical business days in a year, and we're going to simulate this forward for 5 days. So that's why we have 5 over 252. Now we calculate the end price. Now the Excel formula is a little complicated. We just have to be real careful to use the formula as it appears in the textbook. So the end price would be the beginning price times the exponential function, and then in another set of parentheses we'll have mu hat, and we need dollar signs in front of the E2, so we're always referencing that in the same cell. And then we have minus sigma hat squared divided by 2. And then that closes the first set of parentheses, and then we have to multiply that by the delta for the simulation. Now what we add to that, and again I'm still inside the first set of parentheses for the exponential function, is then sigma hat times the square root of the delta for the simulation. And then the last thing that makes this a random ending price is that we multiply it by the cell with the standard normal distribution. And then this parenthesis closes the entire exponential function. So you need to look in the textbook and make sure, convince yourself this is the proper Excel version of that formula. And so that's the ending price after 5 days. All right, so then we'll make that ending price in at-risk an output. Ending price 5 days. All right. Now, let's simulate the price forward 5 months. How would we change the function? Remember, that's actually what we did up here with the multiplicative returns. So it's the same beginning price. We're going to also use a standard normal random variable, so we'll copy that down. But then for the simulation, what we want to use for the delta for the simulation is 5 over 12, because we're simulating it forward 5 months. All right, so now what we need to do is adjust the formula for the end price. So let's go through this one more time. It's the beginning price times the exponential function. In another set of parentheses, we'll have mu hat plus sigma hat squared over 2. And then times the delta. But now we want to use the monthly delta. And you can have dollar signs on these if you want to copy those. I'm not going to copy this one, so it's optional. And then we would say plus the sigma hat times the square root of the delta for the simulation, the monthly one, times the standard normal random variable. And that would be our ending price after 5 months. All right, so now we have our 2 outputs. And so what we want to do is simulate this. I'll simulate it for 2,000 iterations. And we'll just go ahead and simulate, start the simulation. And what we see here is the ending price after 5 months with geometric Brownian motion. Now, what we'll learn here is, that can be useful for a lot of reasons, is an overlay chart. So let's click right here. This says overlays. And we'll add an overlay. And it says select the simulated cells. So I'm going to click on 3 of these cells. I'm going to hold the Control key down, click on the ending price from up above here, the ending price of the daily, 5 days, and then the ending price monthly simulated with geometric Brownian motion. And I'll click OK. And I get the overlay. Now you can expand some of this. I can expand it to see all the values. Now here's what we see. Notice that the blue and red are the distributions. One of them was simulated using the multiplicative log normal distributions. It took 5 at-risk distributions. And then the other one is the price 5 months out, right here, simulated using geometric Brownian motion. And we can see just how similar these distributions are. We can go over here and see that the means are very close. And the other statistics like standard deviation, for instance, is almost exactly the same. So what we see is that this geometric Brownian motion is just as good a method to simulate this price, and it only took one standard normal random variable. And so we'll use this going forward as a way to simplify our models. The green distribution, of course, is the distribution of the end price after 5 days.